Hi everyone and welcome to this demo of ChemSimGuide, an AI-powered assistant built to simplify the process of setting up chemical simulations using Cantera. I am Souvik, a PhD researcher at Western University, and in this video, I'll walk you through how ChemSimGuide was built, what are the problems that it solves, and give you a live demonstration of it in action. This is a project that I have made in fulfillment for the Google Generative AI Capstone. So let us get started. Before we get into the AI assistant itself, let's take a moment to understand Cantera. Cantera is a widely used open source library for simulating thermodynamics, chemical kinetics, transport properties, and reactor networks. It is used widely in the academia and industry for research, and it enables detailed modeling of chemical process systems. As you can see here, there are some examples like reaction networks and vapor liquid systems, and also combustion systems that can be modeled using Cantera, but it can be very challenging to learn and apply effectively. So next we will explore why do we need ChemSimGuide? We know that Cantera is powerful, but it has a steep learning curve. And many of Cantera's users, chemical engineers, production engineers, have a deep understanding of the underlying chemical processes and dynamics. But when it comes to using Cantera itself, they hit a wall. This is because there are a lot of key challenges that they face. Users must navigate extensive documentation, master complex AI object interactions, choose the right thermodynamic and transport models and functions that work for them, and also work with YAML and Python based interfaces. Even really small mistakes like incorrect object sequences or parameter formats can derail progress and cause big errors. On the right, you can see a small snippet for setting up a CSTR simulation, and we can already see it's really complex. And a lot of times, just learning Cantera and then implementing it takes weeks or even months to even get started with it. And what this leads to is that more often than not, a lot of ideas not get implemented or are like terminated after like a few weeks. So this brings us to ChemSim Guide. So why do we need ChemSimGuide? So it is more than just a chatbot. It's a simulation translator and a coding partner for Cantera users. It kind of bridges the gap between engineering knowledge and Cantera coding. Engineers will simply describe their simulation objectives in natural language terms. ChemSimGuide will then map those goals to Cantera's required models, APIs, and object structures. The assistant engages in step-by-step guided setup, asking clarifying questions, simulation parameters, and explaining each component along the way. What sets it apart is that it doesn't just give generic simulation answer, it produces ready-to-execute Python code grounded in Cantera's actual documentation using retrieval augmented generation approach. On the right, we can see the window of how ChemSimGuide session is started and how it looks with the welcome message, and then you will put like the user puts their own query of the simulation they want. So how does it actually work? At its core, it is a conversational AI agent that takes in simulation goals described in natural language and converts them into a structured Cantera simulation setup. It starts by interpreting user intent, like let's say I want to model a methane combustion in a batch reactor, and breaks this goal down into logical simulation steps, like let's say define the gas phase, load the kinetic mechanisms, initialize the initial conditions, and create the reactor and then solve it. So it deconstructs the process, and then throughout the deconstruction, it explains its choices, maps the steps to the correct Cantera API and function calls, and uses a RAG system to pull real examples from Cantera's documentation and explain it to the user and also create code. All of this is powered by Google's Gemini API for reasoning and generation, ChromaDB for fast semantic search over documentation, and LangGraph to orchestrate the conversational flow with function calling. In short, the user will speak the language of engineering and ChemSimGuide will handle the coding for it. So let me walk you through how ChemSimGuide works under the hood using this LangGraph state diagram. Everything starts at the start node, which routes into the central chatbot node. This is powered by Gemini and handles high-level intent understanding, planning, and response generation. From there, depending on the user's request or the agent's reasoning needs, ChemSimGuide decides to choose dynamic routes. It can go to the human node, which is the user, and talk to the user and get more information about the simulation and its parameters. or it can go to RAG tool node where the RAG tool node can access Cantera documentation and give back context to the user and also to the LLM. And the code gen tool node is when the chatbot is ready to produce clean executable Python code, then this tool node is executed and it goes into the documentation and then retrieves information and generates ready to use code for the user. The loop continues, returning to the chatbot node every time until the goal is achieved or the user exits. This graph-based structure orchestrated using LangGraph gives ChemSimGuide robust multi-step planning, memory, and tool execution control, something that makes it more reliable and responsive than a single-shot prompt. All right, now let's switch gears from presentation and dive into the real thing. I will walk you through the Jupyter notebook that powers ChemSimGuide, which shows us how the assistant thinks and retrieves knowledge and generates the code output. So to begin, we load the cleaned Cantera documentation from our Kaggle dataset. This function reads, okay, so this function called load and chunk data reads all the txt files in the folder, then splits the text into overlapping chunks, each around 500 characters long with a 50 character overlap. Chunking is an important pre-processing step for RAG. It allows the system to later embed smaller, semantically meaningful pieces of text rather than the entire document. We also tag each chunk with its source file name, which helps in later stages when we want to trace responses back to documentation. Here, we can see that we load the Kaggle dataset and then create chunks out of it. So there are 14 text files in the Kaggle input folder, and the number of chunks created is 148. This is an example of how one chunk looks, which is like a small output, and then the source is the name of the text file. Now we move into the embedding and retrieval setup. So to convert the text chunks into vector representations, which can later be used for similarity search with the query, we have to define a custom embedding function using the Gemini API. So this is where we do it, is embed content is Gemini's embedding function, and we use the model text embedding, and it takes as input the query. This Gemini function is then put directly into a ChromaDB database. So ChromaDB is a vector store and it's pretty simple to implement. And what we do is we pass this Gemini embedding function to the ChromaDB database, and then in small batch sizes of 50, we pass these chunks, and then these chunks are then converted to embeddings using the Gemini function, and then they're added to the document. Here we can see the number of total entries into the database, which is 148, and it matches the number of chunks. Now this is a small confirmation that RAG is working, which we want to check before we implement it as a tool in our process. So the way we set it up is we put a system prompt to describe what we want, and then we give it a query. I want to calculate the efficiency of a Rankine vapor power cycle, which is a very popular thermodynamic simulation. So now we get the result from the database by querying. We use the query and the number of results or number of chunks we want to retrieve. And what this does is it goes into the database and it looks at the closest chunks of data that are related to the query, and it returns it, and then it gives us an output. So I'm just going to run it. So we can see that we take all the passages and then we pass it to Gemini, and we can get an answer, right? So it gives us a direct answer of the query we put about the Rankine power cycle. We can see here that it directly outputs code without much thinking because this has not been put into an agentic framework yet. But RAG works now. So since RAG works, we will encapsulate the entire RAG into a Python function called search Cantera docs. What this does is it takes a query in and the number of chunks to retrieve, and then it returns. So it looks through the entire database and it returns as an output string all of the chunks, and it is wrapped into a tool which can later be used with LangGraph. This here just shows the specific document, so we can see that the tool invoked is search Cantera docs, the query and the number of results. They found 10 relevant chunks, and these are all the chunks of data. These chunks are then fed to the LLM along with the query, and then the LLM can read through this get context and give us the answer. So now, once that we have the first tool built, we will start building the LangGraph. So for that, the first thing we want is to build the agent state. So this is ChemSim state is a type dict and is kind of like agent's memory. So what it does, it includes the core conversation that the agent does with the user, and also different things like the simulation goal and the simulation parameters, and what are the steps that the LLM has thought of or the user has asked for, and then it just populates this over time as kind of like a memory, and this is what is changed by the LLM after every step. And then once the LLM thinks that it is pretty complete, it uses this context to create like a code. Next thing is defining the system prompt, chemsysint. So this is a system prompt is kind of like the first instruction we give to the LLM, and this in detail goes into exactly how we should go through understanding a simulation using documentation and talking to the user and giving him text guidance, and then also confirm readiness and then handle the code request. And it uses chain of thought guidance for internal reasoning of the LLM. Next, what we want to do is we define the Cantera code generation tool. This is the second tool that we are going to use, and it helps us in generating code for the Cantera simulation, which is the final end goal. So the way this works is we first define a full script generation prompt. This is another system prompt which kind of tells only this tool how to go around making the code and also structure the code logically, set up parameters, define objects. So this is like a instruction to the LLM. And then inside generate Cantera code, it gets a simulation goal, which is a clear description of the desired Cantera simulation supplied by the LLM, and then the number of documents to retrieve. In the first part of this code, it does rag through the documents and then tries to find proper code snippets, and then gets all those code snippets. And then in the second part, this rag context string has all of the code snippets, and it sends it to the LLM along with some other instructions, and it gets the code as an output. Now that all our tools are defined, we will define the agent nodes. The agent has access to two key nodes. The agent has core nodes like the chatbot node, which handles the actual LLM call, the reasoning and planning. Then the human node is what talks to the user and then displays the last message from the LLM and captures the user's next input. We have two other nodes, the RAG tool node and the code gen tool node, which are just wrappers over the functions we already defined. The next thing we do is define the graph edges, which is conditional routing logic. So LangGraph lets us control agent behavior using this logic. And so what happens is after every input, we check if the user has finished or he wants to continue using this node. And should route from chatbot kind of is the main reasoning node that helps the chatbot decide whether it wants to call RAG, whether it wants to call code gen, or whether it wants to go back to the user and then ask him for more inputs. After all of this is defined, we assemble and compile the graph. So we use state graph to build the graph. This is a LangGraph function. And then we add all the nodes one by one and or define all the conditional logics. So this is kind of just like attaching and creating a graph. And then once the graph is created, we can kind of see this is the flow of the chatbot, which I already defined in the presentation. So now the LangGraph is fully assembled and our tools are wired in. We are ready to run ChemSimGuide as a live conversation agent. I will define the LLM as Gemini 2.0 Flash, and then I am ready to give you a live demonstration of how ChemSimGuide works. So we start up the interactive session and we can see that it gives us a welcome message. So I will just use this query and I will show you how it works. So you can see that it already decided to go to RAG, and then it retrieved 5 relevant chunks this time. And then with that, it is asking me for some information that it needs. So working fluid is, I know that it's water. That is something I want to use. But the other things I don't really understand. So I will say, can you explain the, the inputs to me? So you can see that it again goes into Cantera docs and then it searches for multiple things like isentropic efficiency, Rankine cell pressures. So it says maximum pressure, highest pressure reached in the cycle, typically in the boiler, minimum pressure, lowest pressure in the condenser. Isentropic efficiency is it kind of goes into the documentation and gets like really good descriptions to explain to the user what is usually happening in the simulation. So I already have the values. So P max is 8 into 10 to the power 5, and P minimum is 3500 Pascal, and isentropic efficiency. I can say, okay, I do not have the efficiency values. What are the ideal ranges of the value? I already know it should be between 0 and 1, but let's see if it can retrieve this context. So again, it goes and says so it goes into search Cantera docs and says it finds the query is typical isentropic efficiency. And then it says typically zero point 0.7 to zero point 0.9, typically zero point 0.7 to 0.9. So I will say, let us use 0.8 and 0.6. Okay. So once that I have given it, so you can see that it has memorized all the simulation parameters. I'll now ask it just to ground it. Is there anything else that you need before running the script? So it went in and said, yeah, to fully define the initial state, it needs one more parameter, that is the initial temperature, water at the beginning of the cycle. So I will give it, let's say 300 Kelvin, which is room temperature. So now it has everything. So I'll say, yes, generate me the script. So now you will see that it kind of understands that it has to run the code gen tool node, and this will take some time to generate the code. And then you can see that it has generated the entire code for us as a Python code. Now let's say I do not understand a particular part. So let's say I ask it, what exactly is it doing here? Can you explain this code to me? So let's see what it does. See, it again goes in and it tries to come up. So it gives us a very detailed explanation of what exactly the code is doing. And we can now kind of set up Cantera thermodynamic simulations just by talking to this assistant. So now I will quit the live demonstration, and I hope you really liked it. And so now I will move to limitations. So we know that we already saw in the demonstration that ChemSimGuide in its current form can successfully demonstrates that a LangGraph driven agent powered by Gemini can guide users through complex simulations. But it is important to recognize the boundaries of this system. First of all, it is a Cantera only focus. If we want to use it with other things like Aspen Plus, ComSol, OpenFOAM, it simply wouldn't know how to do it. Secondly, its knowledge is only as complete as the documentation we provided, that is the 1520 text files, and anything undocumented could lead to gaps or fallback responses. The biggest issue we have is that there is no real-time execution of the code and validation. It only generates the simulation ready code for us, and then it is up to the user to kind of take that code, run it, and then get the errors and talk back to Cantera. So think of it as like a smart coding copilot. It gets you there faster, but we still have to keep our hands on the wheel. But we have future improvements. We want to bring multiple simulation environment support like Aspen Plus, ChemCAD, OpenFOAM by integrating their documents and APIs. Second of all, we want to build a nice user-friendly chat interface which kind of looks like GPT, so that there is more accessibility and people do not have to work with Python notebooks. And the most important thing is we want to integrate a sandbox runtime like Docker to execute the generated code and provide feedback or error traces in real time. So people don't have to copy paste, run the code and come back and figure that out again. So this concludes the demo. Thank you so much. And If you would like to contact me, you can contact me on my email here and also on LinkedIn. Thank you.